We're now going to motivate the logarithm by looking at exponential equations, so equations involving the exponential function. And our first equation, e to the omega, is I. Ideally, we could take sort of log of both sides, so take log of both sides. We'll see that is kind of a nuanced thing to say, but nevertheless, if we could take log of both sides, we would need to be able to take log of a complex number, right? So log and the exponential functions should somehow undo each other. So let's write that out. Log of e to the omega is log of I, and so omega should be log of I. But we need to learn how to take the log of a complex number, and it has a definition. The definition is it's the normal log, which normally I will always write as ln, but since there's going to be lots of different logs floating around, lots of different symbols, I'm going to indicate this is the real valued log. And we take the real value log, of the modulus, and to that we add I times the argument. And this is sort of all arguments here. This is all arguments. Not just the principal argument, you look at all possible arguments. In particular, log is multi-valued, so this has more than one solution. Now, the modulus of the imaginary number is 1, and the arguments of the imaginary number is pi halves plus any even multiple of pi. This is sort of for all n and z. Log base anything of 1 is 0, so we get I times pi halves plus 2n pi for all n and z. And in fact, we can check this. So let's check it real quick, that these are the solutions. Let's highlight them first. So I claim that these are solutions, and in fact these are all the solutions. Let's just do a quick check. So if we take e to the omega of both sides, or if we exponentiate base e of both sides, we should get I on the right hand side. So this is e to the I pi halves plus I 2 pi n. I'm going to write it like that. And recall that this is the period of the complex exponential. Right? E is 2 pi I periodic, so this is a whole multiple of the period. This is just e to the I pi halves then, which is in fact I. So we did get solutions, so this does work. And in fact, these are all the solutions. All right, let's do another one. So let's look at something with a slightly more complicated modulus. Solve. Oops, let me just write it like this. E to the omega is 1 plus I. So again, we kind of take log of both sides, and we get omega is log of 1 plus I. And the complex, the multi-valued logarithm is log base e of the modulus. This is just a real number now, and we're taking the normal, regular log base e, plus I times the argument of 1 plus I. The modulus of 1 plus I is the square root of 2. So that's just a number. I don't even care what that number is. That's just a number. And then the principal argument of 1 plus I is pi quarters, and all other arguments are whole multiples of pi, 2 pi added to that. So that's for all n and z. And that's it. So these are our solutions. We could go and we could check, but these in fact are solutions, and they are all of them, and the check is similar to the previous one. Let's do the last part here. So C, e to the omega is minus 2, so that means omega is log of minus 2, and log of minus 2 is log base e of 2, which is I'll write it out, so modulus of negative 2, plus I times argument of negative 2. So that's log base e of 2 plus I times one of the arguments of negative 2 is pi, so we do 2n pi. Now in this case, we can write this a little bit nicer. If you factor out a pi, you get 2n plus 1 times pi. And those are our solutions this time. And that's it. That's how you apply the logarithm. And it's The point here to note is that it's multi-valued. So you actually don't get just one solution. You are going to get an infinite number of solutions. This makes sense because the exponential function is not one-to-one. It's kind of infinite to one. And so we should get an infinite number of solutions when we do this.